Hey everyone, welcome back. Today we're going to do a practice problem involving Markov chains. Now this problem is quite long. It has parts A through F, so we're just going to get started right away. So part A asks us to figure out which states, if any, are recurrent, transient, and periodic. So what does recurrent mean? A state is recurrent if for everywhere you can go, you can always get back to that state. So for instance, let's focus on the state 3. One possible place you can go to from 3 is 4. But once you go to 4, you can actually never get back from 3 because you're always going to be, get back to 3 because you're always going to be looping around over here. So 3 is not recurrent. Now let's look at 2. 2, if you go to 1, you can go back to 2 by taking this arc. From 2, you can go to 2, and of course you can get back to yourself that way. So if you start in 2, everywhere you can get to from 2, namely 1, you can always get back. So 1 is recurrent, and by symmetry 2 is recurrent. So let's start writing stuff down over here. Oops, this marker is not good, so let's do pink. So for part A, we have that recurrent states so far are 1 and 2. We said 3 wasn't recurrent, and hopefully you guys can eyeball pretty quickly that 4, 5, and 6 are recurrent. So anywhere you can get to from 4, which is essentially only 5, you can always get back to 4 by going 6, 4. Same thing holds for 5 and for 6. So we have 2 recurrent classes, 1 and 2, and 4, 5, and 6. Okay, so what transient means, it's very simple. You're transient if you're not recurrent. So the only state here that wasn't recurrent is 3. So 3 is our transient state. And periodic states, you guys probably know this already, would be 4, 5, and 6. Because essentially if you're in state 4, you transition to 5 with probability 1 on the next time step. If you're in state 5, you transition to state 6 with probability 1 on the next time step. It's sort of predetermined once you get into this part of the chain where you're going to be at a particular time step. Okay, so part B. Part B asks for the probability that the process is in state 3 after n trials. And one thing that I should emphasize, we'll do this in a different color, is that we're told that the process starts in state 3. So let's see if this color works. Okay, great. So the notation we use for that is x0 is equal to 3. So x is the state, and this subscript has to do with time. And this essentially says that your initial state is 3. So initial state is 3. All right, so given that the chain starts off in 3, what is the probability that you're still in 3 n time steps later? So let's think about this a second. If you are in 3 and you go to 4, you can never get back to 3, right? Similarly, if you're in 3 and you go to 2, you can never get back to 3. So for the process to still be in state 3 after n time steps, the only place you can go is state 3 itself. So using that reasoning, this probability is simply 0.2 to the n, because we're requiring that on every single time step, the transition that the process takes is this arc. And of course, conditioned on being in state 3, the probability that you take this arc on every time step is 0.2. That's sort of the definition of a Markov chain. Okay, so moving right along, part C asks for the expected number of trials up to and including the trial on which the process leaves state 3. So let's do some notation. So let's let W be the number of trials up until the trial on which the process leaves state 3. So hopefully many of you already see this, but my claim is that W is actually a geometric random variable with probability of success of 0.8. So one way to view this, so let me just write down what I just said. So it's geometric with parameter P is equal to 0.8. Okay, so as I was saying, another way to see this is you start in state 3, and the game we're playing is that in every time step, you flip a coin. If the coin lands tails, you stay in state 3. If the coin lands heads, you leave state 3. Except this coin is not fair, it's biased. So let me write that down. I don't remember what I assigned heads, but let's just say heads means you stay in 3, and tails means you leave 3. And so this coin is biased because you stay in 3 with probability 0.2, and you get tails you leave if you go either here or here. So that happens with probability 0.8. And so hopefully you understand that there's sort of a direct mapping between this problem, the problem of the process leaving state 3, and of this process where we start flipping this biased coin, and we want to figure out what's the first time that we get a tails. So we know that the expectation of a geometrically distributed random variable is just 1 over the parameter p, which in our case is 0.8. So we get 1 over 0.8, which is simply 5/4. So our answer to C is 5/4. So I'll let you guys read part D while I'm erasing. I'm going to switch colors to make things more interesting. So part D asks us to find the probability that the process never enters state 1. And we're going to solve this problem in 2 different ways. So hopefully you agree with me that if we start in state 3, if we transition over here to the right, we don't enter state 1, right? Because this is a recurrent class, so you can never get out of it. Now, if you transition from 3 to 2, this is a recurrent class, so you're stuck here forever, right? My claim is that if you go over to this part of the chain, if you move left from 3, you will, at some point, enter state 1. And the reasoning is as follows. If you transition over here to 2, the only way you can avoid 1 is if you keep transitioning from 2 back to 2. So the probability of you doing that is sort of similar to part A, is 0.4 to the n, right, where n is the number of trials. And 0.4 is less than 1. So if you raise a fraction to the power of n and increase n to infinity, this number actually goes to 0. So if you do transition over here, the probability of you eventually hitting state 1 goes to 1. So because of this, the probability of the chain never entering state 1 is actually equivalent to the probability that the chain never moves left. Okay, so let's write that down. Probability you never, and of course everything is conditioned on the fact that x0 is 3, but since I wrote it up here, I'm not going to keep writing it. So probability you never enter state 1 equals the probability you never go left. And by go left, I mean you transition from 3 to 2. Probability never go left. Okay, and so the probability that you never go left is actually 1 minus the probability that you do go left, right? So let's pause here and try and compute this quantity here. And I said we were going to do this in 2 ways. Right now I'm sort of doing the longer way. And then when we finish with this, I'll show you a shortcut. So the probability that you do go left can be calculated in the following way. You could go left on the first time step, and that happens with probability 0.5. Or you could go left on the second time step. That happens with probability 0.2 times 0.5. because you have to get rid of one time step by doing a self loop at 3 and then transition over here. And of course, you don't have to worry about going to the right, because if you go to the right, you never get back over here. So you have plus 0.5 times 0.2. So plus the probability that you go to state 2 on the third time step. To go to state 2 on the third time step, you have to self-transition here twice and then take this branch once. So that gives you 0.5 times 0.2 squared, and of course you see the pattern. You get 0.5 times 0.2 cubed, ... So we can factor out the 0.5, and you end up with a geometric series, 1 plus 0.2 plus 0.2 squared, etc. And if you don't know this fact, don't worry. You know, you can look it up on Wikipedia. It's just a formula that many of you may have seen. If you have a series like this, the sum actually converges to 1 over 1 minus 0.2. Again, I imagine many of you know that, but if you don't, just take that as a fact and don't worry about it. So this is equal to 0.5 over 1 over 0.8, right? And of course, this is equal to 5/8. So this was our answer for the probability that you do go left. So we plug it in over here, and we get that this is 1 minus 5/8, or 3/8. So we have discovered that the probability that you never enter state 1 is equal to 3/8. So we're done with part D, but I promised you a faster way of getting to this answer. And so the reasoning is as follows. The probability that you never enter state 1 is the probability that you never go left. And sort of by a similar argument as we used in part B, after a long time, the probability that you stay in 3 is essentially 0. So stated in other words, at some point after you started running this process, you will go either left or right. And when you do go left or right, you go there with those relative frequencies. So what this is saying is 5 out of 8 times you go left. 3 out of 8 times you go right. That's sort of what these fractions tell us. So you can, you have your answer right there. The probability that you go right is 3 over 8. And so if that intuition makes sense to you, that's a much faster way of getting the answer. So let's just record this here before I erase. We got 3/8. Okay. Now part E, we want the probability that the process is in state 4 after 10 trials. Again, conditioned on the fact that you start in state 3. So let's play around with this a little bit and see what happens if we were to transition to state 4 on the first trial. So that means we're here on 1. That also means we're here on 2, here on 3, here on 4, here on 5, 6, 7, 8, 9, 10. So we found out that if you transition to 4 on the first trial, you are in state 4 on the 10th trial. So that happened with probability 0.3, so we're going to add that there. So probability process in state 4 after 10 trials was equal to 0.3 plus, so this 0.3 again came from the probability of transitioning to 4 on the first trial. Now let's condition on us transitioning to state 4 on the second trial. What happens then? Well, that means we're here on 2, so we're here 3, here 4, 5, 6, 7, 8, 9, 10. So if we transition to 4 on the second trial, we will definitely not be in 4 on the 10th trial. Now, what if you go here on the third trial? So then we have 4, 5, 6, 7, 8, 9, 10. So we're not there. That doesn't work either. Well, what if you transition here on the fourth trial? Then you get 6, 7, 8, 9, 10. Did I do that wrong? 4, 5, 6, 7, 8, 9, 10. Yes, I did that wrong. So you will end up here if you transition to 4 on the fourth trial. So what's the probability of transitioning to 4 on the fourth trial? Well, you have to go here for 3 trials and then here on the fourth. Of course, you can't go that way because if you go that way, you can't come back over here. So we get a plus 0.2 cubed for the 3 self-transitions, and then times 0.3. And now hopefully you see the pattern. So this was if you get to 4 on the first trial. This is if you get to 4 on the 4th trial. And you can probably see the pattern. The guy has a period of 3, and so it's not shocking that the first trial and the 4th trial are 3 apart. So let's see what happens if you get to 4 on the 7th trial. Then you're here on 7, you go 8, 9, 10. So that works. So that was the 7th trial. So you have 0.2 to the 6 times 0.3. And then, so this is get to 4 on 7th. And we'll do one more for fun. So if you got here on 8, you go 9, 10, 11. Oops, sorry. If you're here on 8, you go 9, 10. You don't work. Similarly, 9 doesn't work, but 10 does work. You could, of course, transition to 4 on the 10th trial. And that happens if and only if you go here, you self-transition on 3 9 times, and then you go here on the 10th. So that gives us plus 0.2 to the 9 times 0.3. And so this actually is our answer, and if you do out the arithmetic, you'll get that that's equal to 0.3024. I guess I'll start a new column over here with our answers, 0.3024. And now we just have one more, part F. So for part F, we were asked a similar question. So we want to now condition on the process being in state 4 after 10 trials, and then compute the conditional probability that the process was in state 4 after the first trial. So the probability that the process is in state 4, in state 4 after the first trial, given that process is in state 4 after 10 trials. So this, by definition of conditional probability, is, and for brevity, let's call this A, and let's call this B. Using the definition of conditional probability, we have that this is the probability of A intersect B divided by the probability of B. And we also have that we computed the probability of B in part A. So we can go in and plug in the denominator. So that's 0.3024. So now we just have to compute this numerator. But if you are in state 4 after the first trial, due to this periodicity, you will be in state 4 after the 10th trial. So essentially what I'm saying is A implies B, because if you're here on 1, then you're 2, 3, 4, 5, 6, 7, 8, 9, 10. So this probability is actually simply, this is equal to P of A, and P of A is equal to 0.3. So this is 0.3. And if you do that arithmetic, you get 0.992. And so that actually wasn't too painful. We are now done with this problem, 0.992. So hopefully this has gotten you more comfortable with working with Markov chains. And there's a lot of fun tricks that you can do. We saw how to pay attention. Some things are, this guy was the expectation of a geometric random variable. This guy, we used the idea of relative frequency. We knew that a long time later, 3, you have to eventually transition from 3 and either go left or right. And it's these probabilities that govern the relative frequency with which you go left and right. So that's how we got 3/8. Yeah, so this was a good review, and I hope you enjoyed it.